believe I've mentioned on multiple occasions the importance of molecular orbital theory, and this is no exception. Alright, so let's take a look at what these molecular orbitals actually look like. Alright, so again, they have to adopt this anti-periplanar arrangement. Okay, so I'm going to draw it kind of nice and big to show you when we adopt this anti-periplanar arrangement, okay, in the plane of the paper, and they're anti. Okay, we're going to have groups like this. Each carbon has two things in the plane, and then one coming forward, one going back. So let's draw these ambiguous groups here. R2, R3, okay. So if we actually look at these molecular orbitals that are involved here, okay, I'm going to kind of draw just our general bond. And we will fill in these ones first. R prime, R, okay. Fill in these. R triple prime, R double prime. Okay, so the CH electrons here, okay, that molecular orbital looks like this when we have the H there, okay, and so these are overlapped, so they're the same color. So when the base comes in, okay, base abstracts and attacks this proton, okay, what needs to happen then is that these CH electrons have to overlap then with the C leaving group antibond. Okay, so here's that antibond right here, the sigma star of the C leaving group. Okay, antibonding orbital. That's what I meant to say, not antibond. The antibonding orbital. This is what it looks like. We'll color in one phase. Okay, so there's the node there. Here's a leaving group right here. Okay, so this is the antibonding orbital. C leaving group, anti-bonding sigma star orbital. Okay, because it's a sigma bond. Okay, it's a single bond that we're talking about, and it's anti-bonding. Okay, so it looks like this. Again, we have that node in between there, but importantly, notice where it lies. It lies directly parallel or in line with the CH electrons. Okay, so this is a filled orbital. Okay, so this is a CH sp3H sigma bond. Okay, so what has to happen though is that we're going to break this bond with these electrons, right? Because it's these electrons in this orbital that are going to go and fill this antibonding orbital in order to form the double bond, right? Because it's these electrons that are going to go and form the double bond. So it's important then that these electrons are directly in line to be able to fill this antibonding orbital and thus break this bond. Okay, so here I have, again, this is a filled orbital. Here's the unfilled or the LUMO of the system, okay? And we need to go and fill or attack that LUMO to be able to break the C leaving group bond, and this is only able to be done when the CH and the C leaving group are anti-periplanar. Okay, only then are these electrons of the CH bond directly in line right behind the C leaving group, which is where the antibonding orbital is located. Okay, so now, as soon as the base goes in and attacks that proton, we can then have our electrons go and fill that antibonding orbital to break the bond. Okay, so these electrons fill the C leaving group sigma star to break that bond. C leaving group bond. Okay, so this is why we have to have this anti-periplanar arrangement, okay? Because only then are the CH electrons in the right orientation to be able to go and fill the antibonding orbital of the C leaving group. And so now, once we form our double bond, that's how we make it between with these electrons. We fill it with we fold them over to go and form the double bond. And so that is how we have our alkene. R prime, R, and going back here, so R double prime, and up here, so R triple prime. Okay, so this is how we have bonding above and below, and so this is our new double bond C, pi bond formed. And again, this is only because these electrons were directly in line with the C leaving group antibonding sigma star orbital. It's the only way we could populate it. So if they're in this anti-periplanar arrangement, okay? So, in order to break C leaving group bond electrons from the CH sigma must fill C leaving group sigma star. Okay? They can only do so when the H and the leaving group are anti-periplanar. Okay? So why is this a stereospecific reaction? Because it has to take this formation. It has to take this conformation in the transition state. It has to. Okay, that's why we only get one product. Okay? Cool. There's the why. There's the why. Alright. And that's pretty much it for E1 and E2. So let's compare the two, just like we did with the SN1 and SN2. First up are the different conditions. We're going to talk about conditions and characteristics. Alright, E1 versus E2. Okay, first up, how about the base? For E1, a weak base is fine. Right, just a nice neutral base, as in, you know, protonated water, sorry, just H2O or ethanol, weak. Whereas here, it must be strong for E2. Okay, how about the solvent? Remember for E1, we wanted to stabilize that carbocation, and thus the polar product was best. And for E2, right, the polar aprotic was best. That's because we don't want to stabilize. We want things to be bare. Sorry about that. We don't want to solvate the ions, okay? We don't want to solvate them, whereas here we wanted to solvate the carbocation. How about the leaving group? It's the same for both of these. We need a good one. Need good one. Same is true over here. Need good one. Okay. And how about the leaving group substrate though? The degree of the leaving group. Okay, for E1, right, the tertiary was faster than the secondary. For E2, it was the same thing. Tertiary faster than the secondary, faster than the primary. And again, this was because it made the most substituted alkene with the tertiary. Importantly, we will not form a primary carbocation, so the primary one's not even listed under E1. Because again, this is based on the stability of the carbocation. Here it was the stability of the product. Okay, we form the most stable product because it's most substituted if we have a tertiary leaving group. Here we form the most stable carbocation intermediate, and that's why it was the fastest with the tertiary leaving group. Okay. How about the differences in characteristics? Okay. E1 versus E2, and by characteristics I'm saying things like rate. What does the rate law depend upon for E1? Is it unimolecular or bimolecular for E1? E1, it was unimolecular, that's why it's 1, E1. So it's just dependent on that leaving group, right? Because the rate determining step of the E1 is the leaving group leaves from the carbocations. That's the rate determining step. That's the only thing in the transition state. Whereas E2, right, it was all one step, and both of the starting materials were in that transition state. So it was bimolecular, and both of those starting materials are in the rate law. Okay? How about the regiochem, the regioselectivity of the reaction? Okay? For E1 and both E1 and E2, we form the most substituted alkene. Okay, in terms of which beta hydrogen are we going to react with? Which beta hydrogen? We're going to react with the one that gives us the most substituted alkene. Because again, it's the most stable. Most substituted. Okay? And so where these then differ is the stereochemistry. Right? Because E1 was stereoselective. It could choose, and it chose the transalkene more often. Transalkene major. Remember, this was the E alkene. Okay? Whereas for E2, right, it was stereospecific. It didn't have a choice. It only formed one product, and that product is a result of the H and the leaving group must be anti-periplanar. They have to be anti-periplanar, and whatever diastereomer, whatever conformation of the alkene we get is what we get. Whatever they're anti-periplanar in, whatever the product is the only one it gets. Okay? So how can we predict whether it will be E1 or E2? Well, first look at the base. If it's weak, as in nice and neutral, no minus, what is it going to be? Is it going to be E2? No. We need a strong base for E2. So, strong base, as in it has a minus charge. Whoa, sorry. I said, is it going to be E2? Sorry. If it's a weak base, again, it's going to be E1. Because if it's strong, it has that nice bare minus charge, full-blown negative charge. We're going to go and do the E2. Whereas if it's E1, excuse me, it's not going to be strong enough, and so we form the carbocation first. Sorry, I accidentally wrote that down wrong. But again, no minus charge, just nice and neutral, right? It's going to form the carbocation first. Whereas if it's a strong, full-blown negative charge on that base, we're going to have E2. What if it is a primary leaving group? Again, are we going to form a primary carbocation? The answer is no. Okay, I'll write in your homework, no. Okay, because primary carbocations are not stable. Primary carbocations are not stable. So if it's primary, it's got to be E2. Yes, it will be slower than, say, a tertiary or a secondary, but it can only undergo E2 because we are not going to form a primary carbocation. Okay? And it's come up multiple times in lecture, and I've been alluding to it this whole handout, and that's the fact that elimination reactions compete with substitution reactions. I mean, they have the same starting materials, just instead of a nucleophile, we have a base. And so how can we figure out which one it's going to be? Let's save this topic for Monday, because I think this will be worth a lot of discussion. So let's just save this topic for Monday. See you then.